At the heart of almost every high-performance database, there's this constant battle, this fundamental tension between reading data and writing data. Today, we're going to blueprint a really powerful and honestly surprisingly elegant design that just solves it.
Welcome, everyone. So yeah, that question right there, it's one of the biggest performance hurdles in computer science. And the answer? Well, it's kind of brilliant because it completely flips the script on how we normally think about this stuff.
All right, so let's get right into it. What's the actual problem here? Why can't readers and writers just get along in a typical database? It really boils down to one thing: how we handle changes. Okay, so think of it like this. You can have a ton of people reading a book in a library all at the same time, right? No problem. That's shared access and it scales great. But the second someone needs to rewrite a page in that book, they have to lock the whole thing down. And everyone else, all the readers, any other potential writers, they just have to get in line and wait.
And this is exactly what that traffic jam looks like. You get one writer who grabs that exclusive lock and boom, all the readers are just frozen out, completely blocked. In any system that does a lot of reading, this is a massive performance nightmare. It forces developers to write all this incredibly complicated code just to manage the queue.
So how do we fix this? What if we could just get rid of that exclusive lock entirely? Well, the solution comes from a pretty radical shift in thinking. What if, instead of modifying data, we just made a rule against it?
And that right there is the soul of copy on write. It's a super simple rule, but it has these profound effects. Instead of changing a data page directly, you make a fresh copy of it, and then you apply your changes to the new copy. The original, it's left completely alone, untouched, pristine. It becomes immutable.
Okay, so let's sketch this out. What does this whole copying process actually look like inside a B tree? You know, the data structure that's the backbone for so many of the world's databases.
This is our golden rule. Rule number 1, our only commandment. We never, ever change a page that already exists. Simple as that.
So check this out. When we need to update a leaf node down at the bottom, we follow our rule. We copy it and then modify the copy. But wait, now its parent is pointing to the old unmodified leaf, right? So what do? We copy the parent node too, and we update its pointer to our new leaf. You can see where this is going. It's a chain reaction that cascades all the way up the tree until we create a brand new root. And the crucial part is, the original tree is left completely untouched, exactly as it was.
And this whole process, this is where the magic happens. By creating that new root, we've effectively brought two parallel versions of our data structure into existence at the same time.
All the existing readers, they just keep traversing the original tree from the original root. And because that entire structure is now guaranteed to be immutable, it will literally never change again. They don't need any locks or any kind of coordination. They can just read at maximum performance, totally oblivious to any writes that might be happening elsewhere.
Meanwhile, the writer is off working in its own isolated universe, building out that new path up to the new root. It isn't interfering with a single reader. Once that new tree is fully built and saved, the database just does a tiny atomic swap of a pointer to make the new root the current one for all future transactions.
So the bottom line for our millions of readers, the number of locks they have to deal with is 0. A big, fat 0. That whole writer-reader conflict we started with has been completely designed right out of the system.
And this elegant design doesn't just boost performance. It has this incredible ripple effect that radically simplifies the entire storage system.
Because we never update data in place, whole layers of complex machinery just disappear. You don't need a complex write-ahead log for crash recovery because the old tree root is always a consistent state you can fall back to. You don't need annoying background compaction jobs to clean things up, and like we've seen, managing concurrency becomes dramatically simpler. Best of all, since every old root points to a perfect immutable snapshot of the database, creating backups becomes instantaneous and basically free.
And look, this isn't just some theory on a whiteboard. High-performance databases like LMDB are built on this exact copy-on-write B-tree principle. It's proven its power and simplicity in real-world, high-stakes applications.
And this really leaves us with a final thought. This powerful idea that choosing not to change things in place can lead to simpler, faster, and more robust systems, that's a lesson that goes way beyond just databases. It really makes you wonder, where else